Thank you very much, Robert, for the very kind introduction. And thank you all for taking the time to join me this morning as I am on the West Coast. As I talk a little bit about the fairly diverse set of interests that I've been able to explore in the Loveland Group. I've titled this From Raw Materials to Fission Studies because there's no good compact way to describe the unique blend of nuclear chemistry, nuclear physics, and nuclear engineering that Walt is, of course, famous for over his long career and that I've been fortunate enough to experience while here. I'm going to go ahead and start off with my acknowledgements because there's a bunch of them, as well as a little bit of an acknowledgement that a couple of these figures were provided by collaborators or co-authors. I worked literally 2 weeks after my defense. I moved out to Oregon State, and I was very fortunate that Larry Yao, Ashley Pika were 2 members of the group with Walt Loveland, and we all went out to Los Alamos National Lab, where we were able to use the LANCE facility. We have isotopes provided by the Department of Energy, so on and so forth, and we have very generous funding from these people. Additionally, we had some calculations done by a collaborator at LAM, Lucas Sawarski. So just a brief overview of how this talk's going to go. I'm going to give you a brief overview of total kinetic energy release in fission, why it's important, why we study it, so on and so forth. I'm then going to discuss the impact that target making chemistry has on our studies of TKE, and then also discuss some more recent work that I've been doing during the pandemic to keep busy, developing our new data acquisition system based on some hardware from Mesitech and Wiener Planenbaus. So about 200 MeV of energy is given off in the fission of the actinides. The vast majority of it, about 80% of it, is actually released in the form of the kinetic energy of the fission fragments. So the so-called total kinetic energy is just the sum of the 2 fragments. As you can see here, parameterizations of TKE have been around for a while, with this nice parameterization based on a Coulombic model from Viola in 1985, where it fits very nicely along this simple line to a good first order magnitude fit. But this is assuming low energy, poorly excited fission. Although 83% of energy is released in the form of TKE, that remaining 17% is important, with the majority of it being taken up by beta decay energy, prompt and delayed neutron emissions, and prompt and delayed gamma emissions. But I'm going to come back here for the moment to this Coulombic model where we have the z squared over a to the 1/3 dependence, because this is actually a fairly useful approximation that with a fairly simple Coulomb attraction-based model, we can parameterize TKE. Now, this is important because during fission, if you take a ground state 235 uranium, hit it with a thermal neutron, we of course know that the sum of the 2 mass defects, so mass excesses, are greater than the fission barrier, and so fission can proceed promptly. There is competition between prompt de-excitation by neutron evaporation once you get above the first neutron separation value, in addition to this fission barrier, but and there's also some de-excitation potential from gamma rays. Now, this is all important simply because the fissioning nucleus is a dynamic system. When you exceed the fission barrier, you effectively stretch along the prolate axis 2 proto-fission fragments that have charge centers given here. Now, if we take these mildly distorted proto-fission fragments connected by this neck and then suddenly were to snap the neck, they're actually fairly close to one another. And given charges of Z1 and Z2, we would expect Coulombic repulsion to separate them with a fairly high value simply due to their proximity. However, if we increase the excitation of the compound nucleus, we actually force these proto-fission fragments apart faster. And while there's a balance between the Coulombic repulsion, the global Coulombic repulsion and the local surface tension effects, we do in fact see significant distortions form that separate the proto-fission fragments in the compound nucleus at the moment of scission. Therefore, roughly speaking, as we increase the compound nucleus excitation energy, we expect to see a decrease in total kinetic energy due to the decrease in Coulombic repulsion. We can go into more detail, though, and look at the relationship between mass of the fission fragments and total kinetic energy. As can be seen here, there's about a 6% difference in total kinetic energy between perfectly symmetric fission and the asymmetric mass distribution peak. for this example given for 232 thorium by proton-induced fission. As we increase the TKE, though, you can actually see that the clear peaks that we normally see in mass distribution start to wash out, and the influence of symmetric fission becomes much greater. The effect of this basically means that the shell effects that stabilize these peaks, both magic numbers and distorted shell effects, begin to wash out as the nucleus goes from a compact configuration towards the scission point more rapidly. Now, not all charge and mass ratios are created equally from the perspective of distortion. We can parameterize distortion as the simple ratio of the distance between the two charge centers over d naught, where we take d naught to be the traditional Coulombic repulsion distance of about 1.2 femtometers. And we can, if we know the TKE and can make a good approximation of the mass and the charge of the two fragments, we can deduce the d over d naught values as a function either of fragment charge or fragment mass. Now, for low energy fission, relatively low energy fission, this is only a few MeV above the fission barrier, we actually see this really nice W-shaped deformation, d over d naught relationship, as statically deformed and statically stable shell effects around the z equals 50 and n equals 82 to n equals 88 region actually result in less distortion. Meanwhile, we see peaks in distortion at symmetric and very asymmetric values. Oh, that's unexpected. The upshot of this is effectively that if we have an increase in compound nucleus excitation, we increase the amount of energy that goes into distortion and then, of course, prompt decay by gamma D excitation, as well as prompt neutron emissions. But there's roughly constant amount of energy available in fission because the overall fission fragments don't change hugely. I mean, there's a small difference here, but there's still a lot of excess energy in the compound nucleus versus its daughters. And so TKE has to give somewhat there. So with this in mind, we can actually go through our iterative procedure to determine fragment mass and energy from our two correlated kinetic energy fission fragment events. First step was we take the raw channels of the detector and calibrate it by the Schmitt method. We can then estimate mass and charge, assuming conservation momentum and a fixed mass to charge ratio using the double energy method. We can then estimate the neutron multiplicity for a given incident neutron energy and the output mass and charge using the GEF simulation framework. GEF is fairly robust. It gives us large number of statistics that we can run weeks or months in advance. As you can see here, we have a very sharp decrease here, as is typical. But these features also get washed out as incident neutron energy decreases. On an event-by-event basis, we then adjust the energies with the Northcliffe-Schilling tables to correct for energy losses in the foil backing and in the target itself. For fast neutron events, where there's significant linear momentum transfer, we can correct for this. We then recalculate the mass and charge ratio by the double energy method and loop these steps until we obtain a consistent set of mass results. Now it's this step here, adjusting with the Northcliffe-Schilling tables, that really leads us into the first part of this talk, which is the impact of target making on TKE studies. Now there's three main methods to make targets with the actinides. The first is the simplest, solvent evaporation. You make a solution, you put it on your target backing, and you let it evaporate. This does have the lowest chemical purity, but it is incredibly efficient, so it's useful in some circumstances. Molecular plating is also a common method that is used. This is most applicable when you have a small amount of material and you need a very reasonably sized target. And then finally is vapor deposition, which is only appropriate when you have a large amount of material because it's very inefficient. But it is sort of the gold standard for TKE studies, simply because it gives us the highest amount of confidence in the chemistry of the target. Now, solvent evaporation, I'll just mention very briefly, is not good for fission TKE studies. Even after going through our add-back routine, making our best estimates of target thickness and of the target composition, we get this kind of broad mess that is nowhere near the right answer. Additionally, if you look at left and right detectors, where one is through the target and the carbon foil, and one's just through the target, this doesn't look reasonable at all. It's a giant mess. There's not a lot we can get out of that. So to take it, to go to the next little step of detail, I'm going to focus in on the vapor deposition and molecular plating methods. In both cases, we tend to start with actinide dioxides, which are useful shipped solids. With the vapor deposition method, we typically oxidize these uranium through plutonium samples into a nice little solution. This separates them from any lanthanides that are with them. We can then precipitate these with copper and ascorbic acid in the presence of HF to make a nice, clean actinide tetrafluoride solid. Heating in a vacuum, we can vapor deposit these onto a thin backing, make nice, clean actinide tetrafluoride targets with very high homogeneity and very good chemical certainty. Molecular plating, we can also start with a separated stock solution instead, as americium through Californium and other similar isotopes are typically shipped in the form of a chloride solution or nitrate solution. Either way, we dissolve them up or take the solution, and then we can apply a large voltage, about 400 to 600 volts, in the presence of, for example, NN-DMF or NN-dimethylformamide, which is a common organic solvent, and make this actinide organic target on a thin backing. Now, there are some downsides to molecular plating, and it's not always the best possible answer. We don't exactly know what structures we make. It turns out when you apply about 400 to 600 volts of oxidative effect to an organic compound, it tends to break carbon bonds and just make a whole mess of stuff. The best guesses that have been obtained for the structure when uranium is molecularly plated is you get these uranyl hydroxide. This is a uranyl moiety, and this is a hydroxide moiety that just are polymers with a bunch of other carbon and oxygen and hydrogen mess associated with it. With the later actinides, it looks like we have a carboxylate moiety that's fairly common with all sorts of various R groups off there that depend how long you run the reaction for, what voltage you're at. If you look at it funny, it might change it a little bit. Point being, there's not a huge amount of chemical certainty that can go into making these targets, but sometimes they're the best option that you have simply because it is very efficient and does give a pretty nice homogeneous target. One downside is that when you do deposit these targets, there's a chance for crud. Now, crud is basically everything that's in the glass vial with the actinide when it's shipped, as well as anything you add to it with all those decomposition products after 400 to 600 volts are applied to it. And as you can see here, it does really dramatically degrade the resolution of the fission fragments. And so it makes fission fragment spectroscopy much more difficult. This is kind of a trial and error based system. You'll never truly be able to escape the challenge of crud with molecular plating, but you can at least determine its structure using electron microscopy and the like. And future work hopefully will address that, complementing other work in the field. The gold standard for fission TKE studies, though, remains vapor deposition. Now, up here, you see a raw spectrum just calibrated with the Schmitt method to determine the left versus the right fragment energies. As you can see here, one of them is just a little bit lower in energy than the other. That's because one has their fission fragments going through a carbon foil backing as well as through the center of the target. If we attempt to go through and determine the pre-neutron evaporation TKE, that is the total kinetic energy released before neutrons are evaporated off the surface, we can see that we have a nice Gaussian distribution without any corrections. But it's centered, unfortunately, about 7 MeV too low. The accepted literature value put forth by Wagman suggests that this value should be about 170.5 MeV, but we're getting about 163 MeV. Now, if we look over here, we can actually account for this by functionally the two-step correction. On the first hand, we have the blue sample. The left detector is the fission fragments are losing energy through the carbon foil, and that accounts for about 4 MeV per event on average. Meanwhile, both samples, since we assume that the reaction happens in the center of the target, lose about 1 MeV in the target itself along the way. And after making these corrections, we do in fact obtain a very nice value for TKE, which agrees with Wagman's, and we can see in fact that the left and the right detectors do overlap. No funky magic going on there. It's just effective energy add back after loss. Now, since we are dealing with very highly charged, very massive particles, this add back routine is critically important. I know that it's important in other studies too, but we're talking significant percents of the energy in our primary observable lost. So at this point, I'm going to discuss some recent studies on TKE that I had the good fortune of participating in at Lance with the rest of the group. I'm going to focus in on the recent results that we published that I was the first author on 239 plutonium, but then I'll also briefly discuss our measurements of 237 neptunium and 233 uranium that we did at the same experiment campaign. So the total kinetic energy release of plutonium was visited a large number of times in the thermal regime due to the abundance of thermal neutron sources, relatively speaking. In the 1970s, in the Soviet Union, Akimov did a quick parameterization up to about 5.5 MeV, measuring the total of incident neutron energy, measuring the TKE release at each of these points. Now, much of the details are not published in the English language journal and journals, and therefore we rely on Madlin's parameterization of this data from 2006 to draw a line back to the zero energy neutron and say we expect for thermal neutrons about 175.6 MeV total kinetic energy. That's post-neutron total kinetic energy, which is what we actually measure. In 2016, Krista Meyer-Bachtal at Los Alamos National Lab did a similar campaign where her work was directly scaled with the Akimov data. And this data agrees very nicely up to about 5 MeV. Above that point, the TKE increases somewhat, but this is not necessarily unexpected, as this is near the first neutron separation energy for so-called second chance fission. That is neutron emission followed by fission. What was curious, though, is when we get up to very fast incident neutron energy, about 30 MeV, there was actually this slight increase and then flattening in TKE. Now, the whole raison d'etre that we went to Los Alamos and did this experiment when just a few years ago there was a very reasonable experiment done on this subject, because we didn't think that this was a real data point. You see, there is a big issue with the Meyer-Bachtal experiment. This is not intended as a criticism of their work. It's just the nature of the experiment. The chemistry of the target gets in the way a little bit. This previous experiment used an incredibly thick target of about 462.7 micrograms per centimeter squared, and it was of an at least unpublished composition. They may well know the composition, but for the rest of us, it's rather unknown. So that's a bit of a black box on the public side. Now, this is important because if you look at, for example, symmetric fission in 235 uranium, going from a 46 to 190 microgram per centimeter squared target degrades and changes the values obtained for TKE by about 10 MeV. On the previous slide, this is only a small effect. This is only about half an MeV difference. Now, if you draw the line further down versus where we would expect it to be, it is a little bit larger. But the reality is that there's something here that wasn't being considered. We believed that by using a much thinner target with high chemical homogeneity, high chemical purity that we knew the composition of, that we could address this concern. Additionally, rather than doing event-by-event corrections based on the determined mass and charge and the thickness of the detector and so on and so forth, the previous work used a bulk adjustment, just drawing a line to correct the non-backing side to the backing side, or vice versa. And we felt that we could do a potentially better job clarifying that with this experiment. So to accomplish this, we went to Los Alamos National Lab and used the wonderful Lance facility. Lance is a proton on tungsten spallation facility. The proton beam's about 800 MeV, and we get out neutrons that are up to a very significant percentage of that. As you can see here, the neutron spectrum is more or less white. These are funny little bins here, up to about 600 MeV, at which point it does drop off somewhat. We used a plutonium tetrafluoride target on a carbon foil and a pair of 3x3 silicon pin diode arrays arranged at 180 degrees apart from one another in the lab frame. Given that we're talking about a neutron hitting the target, the linear momentum correction is small. It's not non-existent, but it is small. So the folding angle was close enough to 180 that we could just use the lab frame for this. We determined the incident neutron energy by the neutron time of flight method, referencing the photofission peak obtained here from the tungsten block. And with this method, we were able to obtain sub 5% neutron energy resolution across the entire range of 2 to 100 MeV. Now, one side benefit of this is that we can actually use these slow wraparound neutrons that come from a previous micropulse of the proton driver. These are all very low energy neutrons. And for 239 239 plutonium, since it is thermal neutron fissionable, we can get mass distributions and energy out of these results and use this effectively as an internal standard for our measurements, thus determining we don't see any sort of wander or creep in our calibrations. To benchmark our methods, we went ahead and returned our detectors and our apparatus to the Oregon State Trigger Reactor here in the Radiation Center. My office is somewhere right around here. And as you can see here, we obtained very high statistics measurement of the total kinetic energy release at the Oregon State Trigger Reactor here, obtaining 175.64 MeV TKE, which agrees very nicely with Madland. When we look at those wraparound neutron events, post-neutron TKE, after making all the adjustments we discussed previously, we obtain an energy of 175.5 MeV, which is, again, in very good agreement with Madland. Thus, from these experiments, we conclude that we do measure absolute TKE in our experiments at Lance. So if we compare our thermal events with the lower energy events available at Lance, you can see that we agree fairly well with both the Meyer-Bochtal data and the Madland parameterization of the Akimov data. But this is only up to a few MeV, and that's about where it stops. You see, although we have a qualitative differentiation with the Meyer-Bochtal data here, although we can't statistically resolve it. As you can see here, we see a much greater dependence on the second chance fission, increase in TKE, which de-excites the compound nucleus, and so it forms a more compact scission point configuration. And at the 95% confidence interval, we don't see any significant difference when compared with the Meyer-Bochtal data with a logarithmic fit. But unfortunately, we used a very thin target, which means very small statistics. We also used detectors that only cover about 10% of solid angle for each hemisphere, which means that we have smaller statistics again. So the Meyer-Bochtal data benefits from having very large and robust statistics with a lot smaller differences in incident neutron energy. After discussing this challenge, if you will, it's not a problem, but with this challenge with some theoreticians and experimentalists at Los Alamos, we adopted a secondary form of visualization of post-neutron TKE versus incident neutron energy, which is this rolling average fit. So each of these green bins is plus or minus 5% of the it's plus or minus 5% of the incident neutron energy. We bin all those events together, get out the average TKE, and plot them as a rolling average. If we then plot the standard deviation, the fit that we obtained in the previous over here, and then plus or minus 1 standard deviation, there's a few points that actually go well above the 1 standard deviation line, or touch the 1 standard deviation line here. There are 4 events that we can say don't disappear when we change the binning. That is, when we go from plus or minus 3%, plus or minus 8%, plus or minus 10%, these 4 arrows don't disappear. We attribute these first 3 crossings of the 1 standard deviation line to second, third, and fourth chance fission. And as I mentioned, that is correlated with an increase in TKE at these points due to the de-excitation of the compound nucleus. These 2 points here disappear when we attempt to change the binning of this rolling average. But this final increase, well, is the largest deviation above the standard deviation line, and it occurs at very high energy, which confused us because our fundamental hypothesis going into this was that this data point would disappear. And if you do look even at the coarse bin data, we do see a marked flattening out above about 35 MeV that we don't expect otherwise. If we compare this to the best calculations that we could do really quickly, the GEF calculation framework, we can actually see that GEF does not predict an increase in TKE at this point, or even a mild flattening in TKE at this point. That being said, GEF does systematically overestimate TKE by about 1%. It's possible that this is due to its underestimation of prompt neutron emission by about 5 or 10%. GEF is by and large excellent though, and so we're not too concerned about this, but it is a point of improvement. Similarly, GEF does overestimate the variances on the TKE by about 40%, and that's another point of improvement for it. Oh, I should mention, sorry about that, one of the reasons that we're reasonably certain this is a real signal here is because at our highest binning point, about 83 MeV incident neutron mean energy, we do see again a return to the decreased TKE that we would expect, which makes this set of data really curious. More on that later though. From the double energy method, we can obtain mass yields. The raw values are given in green. Unfortunately, because we're using the double energy method, the best resolution we can get is about plus or minus 5 AMU. So if you compare the smoothed fits with the GEF calculated mass yields, we don't have a huge amount of detail, but we do broadly agree with their conclusions. And as you can see here, for low energy events, up to about 10 MeV, we still see the traditional asymmetric fission peaks as most important. It's only once we start getting to higher incident neutron energies, around 20 or 30 MeV, that symmetric fission becomes a big deal. And just as a benchmark again, when we used our Oregon State trigger reactor experiment, we could actually fit Rosa modes to the mass distributions for 239 plutonium. Since we have parameterizations of the symmetric and asymmetric fission pathways due to the fits that we obtained here, we can actually compare the importance of the symmetric and asymmetric fission modes. In this case, we obtained parameterizations for two different domains in incident neutron energy, that of low energy and high energy. Now, the percent of fissions that are due to symmetric fission is more or less constant in our experiment, up to about 10 MeV. By more or less constant, I mean statistically it's indistinguishable from the average value of 6.1%. By contrast, GEF predicts a stronger dependence on incident neutron energy in this region. And as you can see here, this is a nice flat line while this is increasing. Above 10 MeV, though, we do start to see a fairly dramatic increase in symmetric contribution to fission. And our data broadly agree with GEF results and both fit a logarithmic fit the best. Again, we see this as support for our conclusions and support that GEF is a reasonable model to do our neutron evaporation estimations. When we look at the relationships between mass and TKE, though, we have an interesting story to tell. As you can see over here on the left, if we decompose the TKE into asymmetric and symmetric forms, the asymmetric fission branch is more or less constant in TKE up until about 10 MeV of neutron energy. Meanwhile, we suffer from small statistics due to the small fission branch path, but roughly speaking, symmetric fission up to this point is approximately constant in TKE release as well. Once we get above 10 MeV though, this changes and we actually have a very strong dependence, decreasing dependence for the asymmetric TKE. Meanwhile, symmetric TKE is more or less constant, again, suffering from small statistics here. The long story short is that it's not simply due to increasing symmetric fission with lower TKE that we actually have a decrease in overall TKE release, but also that asymmetric fission decreases in TKE as well. Now, if we bring it back to the scission point distortion model, that would imply that we're seeing an increase in distortion, increase in this D over D naught ratio, as we increase the incident neutron energy, increase the excitation energy of the compound nucleus, particularly in the asymmetric fission branch. And as you can see here, if we compare relatively low energy fission events with relatively high energy fission events, we do see near the asymmetric mass maximum at 135, 136 AMU, we do see a dramatic increase in D over D naught. Curiously, we do also see a small decrease in symmetric distortion, but this is most likely an artifact due to small statistics. If we do attempt to attribute the decreasing TKE based on either change in the asymmetric TKE versus the change in the symmetric contribution to total fission, it's more or less constant, where the change in asymmetric TKE is almost purely correlated with change in overall TKE. And it's not until above 10 MeV when both symmetric and TKE of the asymmetric branch really begin to influence things. Really briefly, during the same campaign at Lance, we also measured the TKE release of 237 neptunium. Our data broadly agree with the low energy region, which was only measured up to about 5 MeV by prior work by Hamsch. And again, curiously, we do actually see marked increase in TKE at this point. And just to support the prior slide, we do also see a good dependence on the asymmetric TKE, and even GEF acknowledges this as well. Now, for some unpublished data, we also measured 233 uranium at Lance up to through the same range. 233 uranium, of course, is fissionable by thermal neutrons as well, and we ran an OSTR experiment as well, obtaining a very good agreement with the literature value for this event. Our internal standard with the wraparound region, again, agreed very nicely with our trigger reactor experiment. But what is somewhat curious is that we actually have a putative increase in TKE release as we go from thermal neutrons to about 4 MeV of incident neutron energy. Now, this has been seen with 232 thorium-induced fission. There was attributed to pair breaking of the 232 thorium target. Now, seeing as we have an uneven nucleus here, that's not quite the case. So more work is needed, and I'd love to look into this region a little bit more. If we plot the rolling average of the fission fragment masses, you can see here that we do have clear differentiation in between the asymmetric and symmetric fission regimes up until about 10 MeV, which is borne out by the percent asymmetric contribution here as well, and then increasing symmetric contribution above that point. Now, experiments at Lance predate my time with Walt, and we've measured a few different nuclides of interest. But if you just draw simple parameterizations based on second order log fits to the first 40 MeV of the data collected, which is about where we see things break down, you can actually see that for most or all of these isotopes, above that 40 MeV point, we actually do see an increase in TKE versus predictions. Now, when we first went into this experiment, we were assuming that this wouldn't be here. So naturally, we tried to answer it. The first and most compelling answer that we could come up with was the possibility of protons in the beamline, either from NP reactions on materials in the beamline or near our target, or from just protons that happen to be to get downrange. Fortunately for us, the flight path 15 right at Lance actually has a sweeper magnet, and without the B field, our hypothesis would actually be correct. It would significantly impact our TKE, certainly above about a 50 MeV range. But given the presence of the sweeper magnet, this is no longer a satisfactory conclusion. So if anybody has any ideas, don't be shy. Please speak up. And now for the final part of my talk, I'd like to discuss the recent work that I've been doing to keep busy during the pandemic minor apocalypse, the characterization of the new digital data acquisition system here at Oregon State University. Now, we're using a set of equipment that we've purchased from Wiener, Plein and Baus. For example, this VME 195X crate, and then over here we have the lovely MDPP16 module. Now, we previously used a set of analog electronics to process the data and require coincident fission events. We then fed this into a time to digital converter and obtained from the time of flight method the energy of the neutrons. Unfortunately, as you can see here, we only had 4096 channels to play with, which means that especially for faster neutrons, that is neutrons that appear sooner after the gamma flash, we have an unfortunate coarsening of the energy that we can measure. You can't see it here because it kind of blurs together due to logarithmic scaling, but there's actually big gaps between each of these events here that makes it somewhat uncertain. And as we increase the incident neutron energy, the error due to the binning of the TDC channels actually becomes quite significant, contributes a good amount to our overall error. This timing error is due to the broadness of the gamma flash. Now, with our newer detectors, we anticipate that with 8 times as many channels, we'll get a roughly 4 or 5 times improvement in our TDC channels and thus improve our time of flight measurements significantly. But the MDPP16 doesn't just give us a 16-bit electronics to work with on the timing front. It also gives us 16-bit electronics to deal with on the ADC front as well. Now, we're used to looking at ranges that are just about here to here with our old data acquisition system. Purely fission fragments, anything, if you try to have it any broader, you'll either compress these peaks to be absolutely useless, or you'll just absolutely swamp the system due to timing issues here. With our new system, we can actually resolve both the alpha regime zoomed in here and the fission regime simultaneously. This is with 252 Californian, which only has a single peak and a little bit of contamination on our detector, which we can resolve. But when we put in a thick source, for example, a very real 233 uranium tetrafluorides source, we can actually also resolve the main alpha peak of 233 and its daughters in turn. And as you can see here, they're well resolved from the fission fragments as well. This gives us the capability to do some fun things like looking at competition between fission and neutron de-excitation, if we can then see the secondary alpha at a different energy. Or we can do fun things like look for ternary fragments. Now, this is a bit of a throwback to early days for Walt. Shortly after he arrived at Oregon State University 50 years ago, where we can actually look at ternary fission events and use this to characterize our new detectors, our new data acquisition system using our detectors. Now, ternary fragments are primarily alphas. They're given off at about 90 degrees to the fission fragments, or more accurately, about 80 degrees from the light fission fragment. And so for our experiment, we actually set up a DE detector followed by a thick stopper detector that happened to be, it was a PIPS detector. We then put these at roughly 80 degrees from one set of pin diodes and 100 degrees from another set of pin diodes. And we started irradiating a sample with neutrons from our reactor, and we then developed a new protocol for determining ternary particles. Step 1, just calibrate the thickness of the detector. This is important for reasons that will become clear soon. We calculate the energy for coincident detections, both in the DE-DX detector and in the stopper E detector. We assume, first of all, that since about 90% of the fission of the ternary particles are going to be alphas, we assume that they are long-range alphas with an incident energy equal to the sum of the two detectors. And from this, using Northcliffe-Schilling tables, we calculate the effective thickness of the DE-DX detector for this given energy and the energy loss in the DE-DX detector. We then loop over other potential ternary particles, and whichever has the least deviation in effective thickness versus the calibrated thickness that we obtained with our DE-DX detector, we say, okay, that's most likely the answer there. Historically, these particles were identified by a multiplier spectrum of the total energy times the energy loss in the DE detector. And we can compare these we can compare our results with the multiplier spectrum for comparison. But this is really this step is the key step, and it's what makes this new data acquisition system really pop, because we can flexibly determine parameters both on the fly and after data collection, whereas previously we were restricted to analog logic. As a quick test, using another 233 uranium source, we can actually clearly define the great-great-great-granddaughter, its parent, and its parent from the thick detector spectrum versus the DE/DX detector as well, even though they're all pretty much just mush here in the DE/DX detector. Notably absent, though, is the main alpha decay peak for 233 uranium, which dominates the overall DE/DX event spectrum. This is because we placed a gate here in the thick detector energy to try to block it out so we can look more closely. Excuse me, look more closely at higher energy alpha events. We see this kind of trend simply because the stopping power of silicon increases as we decrease the energy of the alpha particle. So if we then apply this to Californian 252, which only has a single alpha associated with it, it's a spontaneously fissioning source, and about 0.4% of all of its fissions should be ternary in nature. Run it for a few days. If we look for only non-alpha ternary fragments, we can actually see some nice little groupings here along the diagonal. Based on the previous slide where I discussed the range finding routine, if we plot the identified particles, including the alphas here, we can in fact see that long-range alphas constitute the vast majority of the products given, followed by heavier helium isotopes, lithium isotopes, and then boron and carbon, which I grouped up here together separately as we're not looking at specific isotopes here. If we then compare with the multiplier spectrum, we can draw reasonable lines at or around each of these locations and identify them cleanly. This over here is just really quickly the calculated thickness error that we see based on our identified particles versus the calibrated thickness of the detector. In conclusion, covered a lot of ground here, ranging from nuclear chemistry to nuclear physics to nuclear engineering. At the end of the day, if we're going to be measuring fission TKE, you really do need to understand the material properties of your target. Using high quality vapor deposited targets, we have measured absolute TKE for several different mid and early actinides up to about 100 MeV at Lance. And I've characterized the new DNAS optimized for fission TKE in similar studies for use here. For future work, I'd like to look into the local and global structural changes of targets after irradiation, particularly using electron microscopy and some other advanced material science techniques to try to determine what the nature of molecular plated targets really is, what the chemical bonds are, and determine ways we can optimize their yield, maybe even modify them after deposition. I'd like to re-examine the very fast, that is faster than 30 MeV neutron-induced fission, simply because there's not been a lot of work done on it. Lance is pretty much the best place to do it right now, though other facilities may be coming online soon. And we have a lot of unknowns there. We really aren't certain what's going on to increase the TKE at that point. It may be that coincident studies between fission TKE and gammas are necessary, for example. But studies looking at neutrons emitted in the fission process haven't been too helpful on this front, unfortunately. We are hoping to expand our measurement into the later actinides, more to be continued later. And hopefully we'll be deploying our new compact DDAS to measure fission-related observables, working with really hot sources to measure ternary products. I'm happy to take any questions at this time, and thank you all for sticking around.
Thank you. Excuse me. Thank you, Sasha, for this very nice talk. Of course, we invite questions now. Please, if you have a question, just unmute yourself and ask your question.
I have a question.
Go ahead.
How did you handle, I saw that you benchmarked the energy at OSU and then went to LANL, did the experiment. So that begs the question, did the gain change in your electronics when you're going up many thousands of feet in the temperatures?
It is, so that is possible. That being said, the reason that I'm fairly confident this is something real is because even if there was a gain change, even if there was some sort of altitude or temperature-based effect, which I don't mean to dismiss, the internal standard calibration was about, and if you look at those wraparound events, that was about, that's too far back. There was about a 1 MeV difference for the internal standard. That is using our electronics at lands using the wraparound regime. Was about 1 MeV below the first binge data point that we obtained there.
Oh, okay, that's compelling. Yeah.
Yeah, so
you have
I had to do a double take. Yeah.
Yeah. Okay.
Well,
So and then another question is
mixture
about
of energies, but yeah.
Sorry, what did you say last?
Oh, it's a mixture of energies up to about 0.2 MeV incident neutron energy, but all the same, that does not change TKE dramatically enough to really think that it's not a useful internal standard.
How did you treat ballistic deficit and energy loss in the dead layer and things like that?
So the Schmitt method is a reasonable approximation of energy loss of energy calibration for our pin detectors. So there is, of course, always a little bit of a dead layer that's associated with that, but by calibrating with Californian sources that are roughly the same, release roughly the same energy particles, using the Schmitt method, we can minimize those errors. So the fact that we do hit pretty much smack on the data that we obtain, compared with the Madeline systematics, we're fairly confident that does not introduce a systematic bias in our results.
Okay. Any more questions?
Are you worried about edge effects at all with the pin diodes, like incomplete charge collection, that sort of thing?
Not systematically. We do have little bumpers that cut off a small portion of the outside of the pin diodes to help minimize that concern. But at the end of the day, we've obtained very comparable results from column-made PIPS detectors versus pin diodes.
And then, out of curiosity, how far away from the shutter at 15 right do you guys place your chamber?
A couple meters. We actually have a fission chamber in between to measure the overall neutron rate. And so we have to be able to squeeze it in there. And our chamber itself is fairly bulky to provide room to have the vacuum pump on and to have the detectors in there. But it's roughly speaking 1.5 meters or 2 meters from the shutter there. It's about 13.85 meters from the target itself.
Any other questions?
So
Sorry, I have one last burning question, and that's with Krista's data. Of course, you have to be a little bit more careful to talk about Krista's because Walt's group made her target. It was thick and it had lots of the alpha rate was several megabecquerel, I think.
I don't mean to criticize her work, which the paper in anything other than we had this question that we wanted to answer because it was spectacular work, but it does introduce an error that we did want to control for to see if it was still there. And obviously our work has supported hers by and large. So it was a potential source of error that we just wanted to take a look at and control. Walt doesn't remember that target. So I thought it was one of ours as well, but Walt indicated to me that it wasn't.
It was.
There might be some confusion there then, but at any rate, it was a very thick target, and we wanted to make sure we controlled for any biasing that could have had.
And yeah, so the one key part about it that I don't think you mentioned was the alpha rate was megabecquerel, and you have it's much better to have a thinner target. Yeah, so that's So you don't have a problem that she had, which was
no. Yeah, so there were all sorts of problems that were associated with that simply because it was thick. And at the end of the day, we still see this effect. So obviously the work was good. It was just a motivating hypothesis that we wanted to examine further.
I have one question. Thank you for nice presentation. Unfortunately, I was going back and forth with some other meeting. I have a question on targets. So when you deposit, so after deposition, after electroplating, are you heat treating or you're just using as after deposition? Because that might improve a little bit the quality of the target.
It depends on the backing material, on if we have it as a thin target or or thick backing. Most of the time we do, but there is some risk associated with that. That being said, it doesn't really, as you can see, it doesn't make a huge difference for solvent evaporation. This was a heat treated target, and it doesn't necessarily make a huge difference for molecular plating. It does somewhat burn off some of the carbon based cabbage that's there, but at the end, if there's silicon dioxide particles that are deposited over top of it, just crud from the glass that it was shipped in, then there's not too much that we can do there, unfortunately.
Yeah.
So molecular plating is appropriate for many circumstances. For example, super heavy elements where you're trying to where the compound nucleus recoils out, or for overall bulk capture effects where you don't care as much about the exact identity of this mass versus this mass. But if we're really doing fission TKE studies, though, we do want to get the vapor deposit targets whenever possible.
Also, one quick question on this. So this is, I think, this structure that you described, the Californian one. So it's just analogy for the previously published data on uranium oxide, right? Am I correct?
This is very qualitative. Yeah, this is meant to show that there's just a mess of carbon or another carbon, oxygen, Californium, and other miscellaneous things hanging out. There's probably also water associated or co-crystallized DMF or whatever, but this is purely qualitative. Yeah.
Thank you very much.
Happy to help.
Since you're talking about targets, how thin a backing can you actually use without risking to break your target each time you make it?
So it depends on the material that we're using. In principle, if you're doing vapor deposition, as long as you don't cause enough thermal expansion that it breaks the backing with the aluminum or alloy frame that we're dealing with, in principle, as thin as you want. The reality is that with molecular plating, we have lots and lots of runs that we have to do to make sure that we get a good target, even with 100 micrograms per centimeter squared if it's carbon. Okay. That being said, we do occasionally do thinner, but it does take some special handling and probably burning through a bunch of carbon backings and recycling of California to do that. Steady hands make this a lot easier, but at the end of the day, they are thin foils, and we do want to take care of them.
All right. Any other questions? I don't see any. Well, I can only applaud or make a sign, and I need everybody else to do the same through the reaction or something like that. But thank you very much. This was a wonderful talk, and we wish you all the best. And hopefully, we go out of this COVID that you can get on the road and keep doing your experiments the way you would like. Again, thank you very much, and thank you to everybody for joining us. So
Thanks
long.
everybody for showing up. Really appreciate it.
So long. Okay. Okay. Again, this was great. So we recorded it, as you probably are aware, and hopefully you'll see it posted fairly soon. Then.
I appreciate it. Thank you for hosting. This has been a great experience.
It's been very interesting. I'm interested in these targets because we would like to do column excitation on. We have done column excitation on plutonium-240 and 239. Like
using Higgs, right?
We have that was not at Higgs. That was done at Atlas way a few years ago. We would like to get back to studying the strength of the octupole correlations, and we ended up in the end being limited by what we could do because we had to put it on a very thick backing, and we couldn't so that we couldn't do what I call the full Coulomb excitation, where you measure both the projectile and the target, and you try to measure the angular dependence, because that's how you get more information from the Coulomb, and that was essentially impossible.
So much of what we deal with here really does come down to the material properties of the target, and thicker is good up to a point, but then thinner wins out eventually.
And actually, Walt had mentioned to me that if we were going to restart this program, we should talk to him. And I definitely, from what I heard from you here today, that's definitely the way to go. Now, on the other hand, if I want to do something at X, then I need grams.
Yeah, it really does depend, because those photo fission cross sections are pretty small, aren't they?
That's right. That's right. Okay. Hey, again, I've got to run as well. Good luck to you, and let's keep in touch. And let's just make sure that we are together at the next Golden Conference.
I look forward to it.
Unfortunately, that's going to be 23 now, because we had to announce that we couldn't have it this year. And I think the Golden is one of these conferences where if you can't do it,
right, you don't do it.
You don't do it, because it's just not worth it.
It was the best experience I've ever had at a conference by far, which of course is cliche to say, but it was just fantastic.
Look, that's why I think I haven't missed one in at least since the early 90s. I've been to every one of them, and just because of the nature and the spirit of the conference. And so,
absolutely,
we should do it in 23. Hopefully, by then, this is all only a bad memory.
I'm hoping to get a shot soon.
I'm
Same to
looking.
you, Al.
Yeah, I got my second one last Sunday. So
fantastic.
I got the Moderna, and the first one was no problem at all. On the second one, I paid the price. I mean, I had heavy fever for about 10 hours, and then after that, it came quickly. It went quickly, so that's good.
Well, that is very good.
All right. Again, thank you very much, and we'll see you soon. Okay.
Take care, everybody. Thanks again.
Say hi to
I will do so right away.
Bye-bye.